Okay, so we have that the following figure represents a graph of capital F of x and capital F prime of x. Okay, so let me increase the font size here. So this is capital F of x and capital F prime of x. Or in other words, this function right here is the antiderivative of this one. Okay, so then it says shade the region on f prime of x that corresponds to capital F of b minus capital F of a. So it's saying on this function, graph this right here. So this is capital F of b is right here, and capital F at a is right here. So f of b minus f of a, that's the distance from here to here. So this right here is capital F of b minus capital F at a. So the change in there's a couple ways to look at it. This is the change in the quantity and value of this function, which is, if you're thinking of this as the derivative, so this capital F of b minus f of a, that simply corresponds to the integral from a to b of this function right here. Okay, so well, this right here, this integral, that's just the area underneath the curve from a to b. So if you find this, counting of course this one as positive area and this one as negative area, then you would get f of b, capital F of b minus capital F of a. You can also see this, if you use the fundamental theorem of calculus, which says find the antiderivative of capital F prime of x, that would be capital F of x. Evaluate from a to b, this would give you capital F of b minus capital F of a, which is exactly what you're looking for. And that's pretty much it. Okay, so the question here is, which one of these functions is a possible antiderivative of this function? So there are several different aspects of this that you can look at. We can do it sort of step by step, kind of how we graphed the previous problems when we graphed them. And we can say, that's not a very good color. We can say, for example, here it's positive, which means that the antiderivative would have to be increasing from here to here. So you can automatically take out this one because it's not increasing from here to here. And you can also take out this one because it's also not increasing from here to here. Okay, and then on this part, because it's negative here, then for the last half it would have to be decreasing, and so it can't be this one. So this one satisfies those because it's increasing and then it's decreasing. Another aspect that you can look at is you look at whether this function is increasing or decreasing. And so since it's always decreasing, that means that the antiderivative would have to be always concave down. And this one satisfies that as well. And that's it. Okay, so in this function we have a function that represents velocity, and it's asking us, well, which one of these could represent the position of this function? So remember, basically the position is the antiderivative of the velocity. So we can use the similar analysis. Let's go kind of backwards here. Let's use the increasing decreasing nature. So because this one's decreasing, then that implies that the position would have to be always concave down. And so out of these, you can automatically eliminate this one, you can eliminate this one, and you can already eliminate that one, and it would have to be this one because this is the only one that's concave down. And then, just to sort of talk about everything here, it also satisfies the other properties. Here, notice that it's positive, which means that it would have to be increasing. This one is. And here it's negative, which means that it would have to be decreasing, which, again, this one is. Okay, so here we're trying to find the area of the region under y equals e to the x and above y equals 1 from 0 to 2. Now we're going to do, there's an entire section devoted to this topic, but this is sort of a simpler one, and it's a good kind of preview to that one. So let me draw a picture of the function e to the x, so it looks kind of like that, right? And then you have y equals to 1. Let's do light blue for that one. So this is 1. And so this function looks like that. And then it says x goes from 0 to 2. So let's draw that in like that. So 0 to 2. And so the area that we're looking for, it's under e to the x and above y equals 1. And so we're looking for this area right here. Let me do it in red better. So this is what we're looking for. That's pretty. Okay, so we're looking for this area. Now, how could we possibly find this area? What could our strategy be? Well, notice how if you find the integral from 0 to 2 of e to the x, that would give you the area underneath e to the x from the x-axis, right? So it would give you all of that. So that's what the integral from 0 to 2 of e to the x dx would give you, right? But then you don't want this area down here. You just want this one up here. So since you just want that one, then, well, you have, if you find the area underneath y equals 1, you would get that, right? So why don't you, instead of adding to it, why don't you just take that area away? So if you find what that is, you can simply take that area away, right? So you find the area underneath all of e to the x from 0 to 2, and then you subtract the area underneath y equals 1 from 0 to 2, and that area right there is going to equal to, you can just, since it's a rectangle, you can just find it. That's just 2. So minus 2. And so this is just equal to, let me go down a little bit. This is going to be equal to, the antiderivative is e to the x evaluated from 0 to 2, and then minus 2. And this is equal to e squared minus e to the 0 minus 2. So this is e squared minus 1 minus 2. That's minus 3. And that's it. That's the area. You can approximate it with your calculator if you want. But that's this area right here that we colored in. Okay, now we need to find the area of the region between y equals x squared and above y equals negative 1. Interesting. So let's draw a picture of that, see what that looks like. Y equals x squared looks like that. And y equals negative 1, that's down here, horizontal line at negative 1. And from 0 to 1, so that's from 0 to the number 1. So the area that we're looking for is all of that. Okay, so what would our strategy be in this case? Well, let me put in a couple of the numbers. So right there, that's equal to the number 1. Okay, and that's 0. So if we find we can find the area underneath x squared, and that's going to give us this chunk right here from 0 to 1. That's this section right here. And then we're going to add, we want to add this rectangle. Well, what's the width of, what's the area of that rectangle? Well, that's just the number 1, right? So you don't have to do any integration stuff right there. That's just the area of that rectangle is just 1. So whatever the area underneath x squared is, we're just going to add the area of this rectangle right here. So this is just equal to x cubed over 3, evaluated from 0 to 1, plus 1. So this is equal to 1/3 minus 0 plus 1. So this is equal to 4/3. That was even easier than the other one. And that's it. Easy, right?